Hello, everybody. My name is Andreas Kemperlier. I'm an associate professor at the Department of Engineering Science and Biomedical Engineering at the University of Auckland in New Zealand. It's my pleasure to present to you today the Omnibus lecture on activity recognition with systematic time series feature engineering. So imagine the following situation. You want to write an algorithm which is able to distinguish different activities based on example data which you have measured using two inertial measurement units. So here in this example, we are using two IMU systems from the company iMeasureU. It's Blue Thunder sensor systems. These two are synchronized. One is mounted onto the right ankle, one onto the left ankle. And each of these IMUs measures the acceleration in X, Y, and Z direction, the rotational velocity in X, Y, and Z direction, and the magnitude of the magnetic field into these three directions. So this means we've got 9 different time series per IMU system. And due to the fact that the two IMU systems are synchronized, we can also compute the difference of related time series. For example, we can compute another time series, which is the difference of acceleration in X direction from the left sensor to the acceleration in X direction measured at the right sensor. Okay, so both of these, or all of these 6 time series, so we're measuring these differences for the accelerations and rotational velocities. So in total, we get 24 different time series, which we can use to train an activity recognition algorithm. Now, let's have a look at some examples for 2 different activities. So what we're seeing here on these 4 plots, on the left-hand side, we're seeing running, and on the right-hand side, we're seeing walking. The first row is the left sensor showing the acceleration into X direction, and the bottom row is the right sensor also showing the acceleration into X direction. What we're seeing in this running example that we've got 3 peaks on the left column and only 2 peaks on the right column. So, for example, if we want to distinguish running and walking, we could, for example, just count the number of peaks for one of these windows, being an example of the different activities. Now, as I mentioned, we can also use the difference between these 2 sensor signals, between left and right sensor, as an additional input. Right? This is indicated by the by these 5 different red vertical bars, which are connecting the different points in time. But before we use the fact that we can also use the differences, or we can generate new time series by computing the difference, let's have a look at another feature which we can easily manually engineer by looking at the data. And this feature is just the maximum of the signal. So if you look at the X and the Y axis here, so here we've got a magnitude of up to 150 meters squared for running and up to 60 meters squared for walking. So clearly, first of all, these accelerations are much too high. So this indicates that the sensor systems were not fitted tightly enough to the ankles, so they were just wobbling around. Now, this explains these large accelerations. What we have here is very typical that our signal itself is filled with errors, and this is one type of error, right? So the magnitude is too large, actually. Nevertheless, given these measurements, we would be able to distinguish running and walking by saying, okay, if the acceleration is larger than 100, the acceleration in peaks, right, is larger than 100 meters squared, then it's more likely running, and below that, it's more likely to be walking activity. So this would be the manual feature engineering approach. But in machine learning, what we want to do is we want to find these features automatically, or we want just to use the recorded data, feed it into an algorithm, and then come up with a suitable solution for distinguishing running and walking. Now, in this example, in order to introduce the systematic feature engineering approach, let's start with naive feature engineering first. So let's assume we just take into account one signal, namely the acceleration into X direction. For example, this signal here. So we've got a time window, approximately 2 seconds here in this example. And we can use all these measurements as one row of our naive feature engineering matrix, right? So this is an example for running. This could be the first row of our naive feature engineering matrix, all these measurements. And this example for walking here, all these measurements could become the second row of our feature matrix. So the naive feature engineering matrix has as rows all the measurements from one specific time window for which we have a label, right? And the columns are all the measurements measured relative to the beginning of the window. So this is the naive feature engineering approach. And most deep learning approaches use these type of matrices, but needs millions of rows in order to learn the features first and then learn the discriminator for the different classes. But in engineering applications, we only have, most of the time, a few observations. And few means a couple of hundred up to 1,000. Now, if we want to learn something from this reasonably small number of observations, it is more efficient to come up to describe every observed window with respect to features. Like, for example, the maximum for each window or the number of peaks for each windows. So this is very similar to defining a library of functions. So here we've got capital K many functions, one of which is compute the maximum of one input signal over the input time window, or count, another function could be count the number of peaks per window. However, in order to make this more comprehensive, there are predefined libraries, like, for example, provided by the Python module tsfresh or the MATLAB module HCTSA. And these libraries have collected suitable algorithms which have been found to be useful in some other kind of time series classification or regression algorithm. So in tsfresh example, for example, capital K is 800 or around 800. So 800 different characteristics are computed from each input time window, each observed window with some sensor signals, and are becoming a column. Each of these functions applied to the input time series becoming a column of the engineered time series feature matrix. Right? So every column here is one specific function applied to one specific sensor signal. And every row is now the collection of all the different characteristics which we have computed. Now, in the previous example, we just had talked about using the data from the acceleration in x direction of the left sensor, right? But we have got in total 24 different signals, right? 9 sensor signals per sensor unit, and in addition, six signals for the differences. Now, what we can do, this would mean that we would just get another set of 800 features for each of the input time series. Right? So the matrix would just become larger and larger. Now, given the fact that we've got so many different characteristics which have been computed from a default library of algorithms, many of those features are not relevant, are just noise, and are not helpful for our machine learning topic or problem at hand. And here in this example, the problem is to distinguish running and walking. So in order to prevent overfitting, we need to get rid of all those noisy features which are not helpful. And this is when the feature selection becomes important. So in this time series feature engineering context, the definition of relevant feature is as follows. Let K be the column index of our feature matrix X5 and assume n feature target pairs. So we've got a feature value and the associated activity, so either running or walking. And I is now the label of that specific window and the associated activity. Now the feature xk has all the values of this specific feature for all the observations, right? And we're using this feature to make a statement if it's relevant or meaningful for predicting the target. And here the target would be a collection of the different activities which are associated with one of the observed windows. So we've got capital N feature values, capital N target values, and now the idea is if feature is relevant or meaningful if and only if feature xk and target vector y are not statistically independent. This means if fxk is the probability density of feature xk, and we are computing the conditional distribution of this density, then if we condition this on one activity, for example, walking, so C1, this density, this conditional density, needs to be different from the density conditioned on the other activity running. So if these two conditional densities are different, then we know that this specific feature is relevant or useful for our machine learning target intent. Now, in this specific example of discriminating running and walking, this can be seen in the scatter plot. So here we have picked two time series features, which will be discussed later. And we have created a scatter plot showing the two different activities with different colors. So the black dots refer to walking and the blue dots refer to running. And we clearly see in this two-dimensional feature space, there's a clear line which we can just plot as heuristics to discriminate walking and around the origin, all these plots, and running are the blue dots scattered to the top right of this diagram. So it's very simple, but this means that both of these features are relevant, right? And the conditional probability densities are statistically independent, right? Because the scatter plots of blue and black dots are not overlapping, but they are clearly separated in this feature space. Now, you can do this, of course, manually, right? But it's very tedious to do this for thousands of features, which you have easily when you compute 800 features for 24 different input time series. So therefore, everything has been automated, both the feature extraction and the feature selection. And this automation is the so-called fresh algorithm, which needs to be integrated into the systematic time series feature engineering process. So what's the idea? So first of all, you need to collect labeled time series and relevant univariate variables. So in this example of activity recognition, the univariate variables would be, for example, the height or weight of a subject. So if we had several people who were recording running and walking activities, we could collect these data and add these as additional columns to our feature matrix. Now, given the computed time series features and these univariate variables, we can extract the statistically significant features and just continue with these features, right? Everything, and the idea for computing the significance or statistically significant features is basically using hypothesis tests and control of false discovery rate, similar to or using the definition shown on the previous page. Now, if we have got this set of statistically significant features, we can develop a machine learning model and identify relevant features, because many of the extracted features which are significant still will be collinear, and so we want to get rid of the collinear features. And if we have just identified the relevant features, we can retrain the model, especially if we can neglect concept drift, and just use these features, the identified relevant features for our deployed model. And of course, we always need to monitor performance to be guarded against concept drift. However, in many applications, we observe, especially in engineering and medical applications, that we've got imbalanced data sets. In this case, we found that undersampling the problem works quite well. And then working or training the algorithm on the undersampled problem gives quite powerful classifiers. Now, let's go back to the two features, right? Feature 1 and feature 2, which had been identified as some of the most relevant features for discriminating running and walking. So on the x-axis, feature 1 is this specific feature with this incredibly long name. So this feature has been computed using the Python library tsfresh, and tsfresh has a consistent naming scheme. So the first part of this name, everything before the 2 underscores, is the name of the input time series. So what we're seeing here is the time series gyroscope in Z direction, so the rotational velocity in Z direction of the left sensor systems. The function which has been used to compute this feature is called change quantiles. This is basically something computing the conditional dynamics. And then we've got 4 parameters which have been used to parameterize that specific function. And we don't have the time to really look into the interpretation of this, but it basically means that we are discriminating we try to estimate the next change of our time series if we are in a specific point in the state space, right? So we restrict, basically making a conditional forecast what's likely to happen next. And we are expecting that the changes are larger if we are running. So this is why the feature 1 has running activity more on the right-hand side of the scatter plot. And the second feature, the y-axis, is computed from the acceleration in Z direction, also from the left sensor. And here we are having the aggregated linear trend. So this is basically, the idea is to decompose every input time window into smaller subsets of 10 values, fitting a linear model to this, and then overall, for each of these linear models, computing the standard error, which we obtain from the fitting linear model, and from all the standard errors of these piecewise linear models, we take the minimum. So the smaller the standard error of those piecewise linear models, the more likely is that it's walking. Right? This is why we see all the walk activity here at the close to the origin. And this, of course, makes also sense. Now, the key thing is these extensive feature names allow us to interpret the features themselves, right? So we can give a meaning to the features and can understand what the algorithm, which property of the time series the algorithm has learned to distinct running and walking. So this points towards explainable machine learning. Now, given the subset of relevant features, and a model which had been trained onto different running and walking activities, the student in this example had recorded another section where he was alternating between running and walking, and then applied the trained model, which had never seen this data before, to discriminate running and walking. And what we're seeing here is there was a short exercise of 30 seconds. And on the left-hand side, we're seeing the probability the algorithm has assigned to a specific window that it's either running or walking. Green refers to walking, blue refers to running. And we see the student starts with walking, and the algorithm correctly has assigned the probability of 1 because it was a walking activity. Then the student started running after 1 minute approximately. And at the very beginning, he seemed to run quite slowly. So the algorithm thought it still might be walking. But then the student sped up and everything was correctly identified as running. Only the exceptions are afterwards the switch from between running and walking, which makes sense. So this is basically an out-of-sample evaluation of the trained activity recognition algorithm. Now, this is just one example, right? We had talked about, and the workflow is always do the time series engineering, so create new time series, for example, the differences of 2 synchronized sensors, do the feature extraction and the feature selection, both of which is integrated into the TS-Fresh package. Then model your supervised machine learning and apply this to different applications, right? So, of course, should be IID'd into a data set which always is very similar to what has been used for learning. But this can be extended. For example, this is another activity recognition example where 8 different activities had been predicted after being trained on the activities of 5 persons, right? And the 6th person was evaluating this, and the performance was quite accurate. But this approach of feature engineering does not only work for time series. All types of data which have some type of internal ordering are suitable. For example, spectra, right? The ordering dimension of spectra is not time, but wavelength, as here. This is the absorption of the organic solar cell, of some example, organic solar cell. And you can extract time series features or features from these spectra and train algorithm to estimate the thickness of the organic solar cells. And if you know at which location of the organic solar cell the thickness was estimated or the absorption was measured, you can create a map, a thickness map of an organic solar cell, which does not need to destroy the solar cell, right? If you have got a couple of calibration measurements which map these spectra to the respective thicknesses. And here in this example has been taken from a spin-coated organic solar cell. You clearly see that at the rim, the thickness is higher compared to the center, and there are also some defects, right? These blue points here, where no coating really stuck to the surface. Another example, we've got ordered data which are not time series, comes from image classification, right? So here in this example, we've got satellite images which had been which are used to discriminate properties with pool and properties without pool. And here we've got a modified swimming pool index, which has been computed using the blue signal, or the blue channel, and the near infrared channel of the remote sensing images. And if we take or concatenate all the rows of this image, we get a spatial variation sequence. So the first row comes at the very beginning, then we're adding the second row, we're getting a long vector, one row of the image after the other, right? And if we're using this as input to TS-Fresh, we clearly see here in this example that this sequence of peaks, or this pulse train, refers to the pulse to the pool over here. So every time the row crosses the pool, we're getting a pulse over here. Feeding this into the feature extraction algorithm, we find quite a nice and straightforward classification algorithm which can distinguish properties with pools and without pools. Right, so this is here one example of these conditional distributions where we can discriminate pools and not pools from those images. And an even more extreme example of engineering time series comes from natural language processing. So if you want to discriminate, for example, the writing style of authors, you could use an approach which takes a sentence, and for every word in that sentence, counts the number of letters in that word. Now, if you've got enough examples, right, you can, from each of those, if you count the number of letters per word, you get a sequence of word lengths. And again, you can run these word length sequences through the feature engineering process, and then get basically something which describes the writing style of the author. So we've done this for 3 different authors, and the feature space was a little bit larger. So we did perform, or we reduced the dimensionality and projected this into a feature space using principal component analysis. And the different colors in this example on the bottom right refer to one of the 3 different authors, right? And we clearly can see there are regions in this space, in this principal component space, where it's more likely that the blue-coded author has, or that this specific sentence or specific sentence in this feature space would have been assigned to one of the authors compared to the other regions. So you can discriminate the writing style of authors using sentences via engineering of time series and the feature engineering approach to get some insights into the style of authors, the writing style of authors, and discriminate them. Now, let's wrap this up. Systematic time series feature engineering combines two different disciplines, the automated time series feature extraction and feature selection, right? Both together give you systematic time series feature engineering. Now, due to the fact that the machine learning libraries for systematic time series feature engineering, they actually complement the machine learning toolbox, right? There are the TS-Fresh package and HCTSA, and these are two examples. Now, but you don't have to worry about manually engineering features from time series anymore. You just use these libraries. And this means you can now think about which time series should I design, or how should I engineer my input time series to get relevant features for my process. So we have got a shift from time series feature engineering to the engineering of time series, right? Very similar to these examples where we engineered spatial variation sequences or these word length sequences, which can be used for feature engineering. Now, the automation of feature engineering speeds up the experimental validation and operationalization of new sensor systems, and it's well suited for problems with small sample sizes. So it's very relevant for engineering applications. If you want to read more about these approaches, please have a look at these two papers, which are referenced here. The first one introduces the Fresh algorithm, and the second one describes the Python library TS-Fresh, which has been published to implement the Fresh algorithm. Now, all this work wouldn't have been done with the participation of an awesome team of people, right? So many thanks to all my contributors, especially the team about Michael Feind, who Michael Feind came up with the idea of the Fresh algorithm, and Max, Niels, and Julius have written up the TS-Fresh library, and my colleagues and students who have worked on all these different applications. And of course, there has been a huge community of TS-Fresh users which are using and contributing to the development of TS-Fresh. So many thanks to all of you. It's really great to be part of this huge community of time series machine learning enthusiasts. If you have questions, shoot me an email. Happy to chat. And I want to finish this Omnibus lecture with a small quiz. So the presentation has discussed two different feature engineering approaches for machine learning models using time series as input data: naive time series feature engineering and systematic time series feature engineering. Now the question: which of the two feature engineering approaches can process input time series having different numbers of measurements per observation? So let's assume the following. The first observation has capital T1 measurements, right? And then the second observation has capital T2 many measurements, similar to this example where we had created word length sequences, right? Every sentence has a different number of words. So every observation, every word length sequence has a different number of measurements. So which of these two approaches can be used for if in these types of situations? Think about it. And press the pause button before you click to you continue and see the answer to this question. Now the answer to this question is given on the following slide. Systematic time series feature engineering is the correct answer. It projects the time series into well-defined k-dimensional feature space, irrespective of the length of the input time series samples. And this is very, very important because it gives you a robust representation of your observation, irrespective of the numbers of measurements which you have. So, of course, you could work with imputing, but there are always situations where imputation doesn't work. For example, the example with the natural language processing, where we had word length sequences as input signal. So systematic time series feature engineering is quite useful. And if you want to read more about this and applications where we had different number of measurements per observation, have a look at these two articles which make use of this feature of systematic time series feature engineering quite heavily. So thank you very much for your interest, and have fun with using systematic time series feature engineering.